much for this wonderful introduction and also for inviting me to this conference. I'm really enjoying being here on this beautiful campus of UM6P. The International Space Station is a marvel of technology, but I'm interested in it to consider its social implications. After all, this is probably the most expensive structure built by humans so far, and it has involved in its creation a very large-scale degree of cooperation. Cooperation not only within nations, but at the international stage, including such rival powers as US, Russia, and many others. So the estimate is that perhaps 3 million people years were involved in creating this structure. So this is a visible illustration that humans are capable of cooperating in huge groups of strangers, people, or even people who have never met each other. What's interesting is that this capacity is very recent. If we look and go back through history by looking at impressive structures, such as the Empire State Building, the Cathedral of Amiens, and so on and so forth, what we see is that as we reach into the deep past, we may see the impressive pyramid of Giza, roughly speaking, 4.5 millennia ago, which involved, whose building involved, let's say, tens of thousands of people over many years. And then eventually, as we keep drilling back into the past, we'll get to Göbekli Tepe, about 11,000 years ago, whose creation involved perhaps 500 people or so. And beyond that, nothing. But human species is much more ancient than 11,000 years. Different estimates vary, but roughly speaking, we have been around for 200,000 years. So for 95% of our history, humans lived in small-scale, relatively simple societies organized as foraging bands or ethno-linguistic groups of, roughly speaking, some hundreds or low thousands. And then 10,000 years ago, something happened, and the social scale at which people cooperate and the complexity of human society started to increase. So about 5,000 years, we see the rise of the first states. And you can see in the left-hand side, in the left-hand column of this table, a very rough estimate, really an order of magnitude of the number of people involved in various polities, political systems ranging from independently governed farming villages to mega empires and large nation states. So what we see here, it's roughly speaking 6 or 7 orders of magnitude. This is a truly astronomical change. It's so many orders of magnitude that has characterized social evolution of our species. And at the same time, of course, there was quite a lot of institutional development that I'll be mentioning later in my talk. So to me, this is the basic fact of social science, in fact, that human societies have increased so dramatically in scale and in institutional complexity. In the process, we became the champion cooperators on Earth. Our nearest rivals are social insects, such as leafcutter ants, who these colonies number in millions of individuals, have very sophisticated economy, including agriculture, and very complex social organization. But if you think about it, we have, and so these social insects have been around for tens of millions of years. Say ants have been around for 90 million years. And until, let's say, 4.5 millennia ago, they were unrivaled cooperators. But we have exceeded them in the last 4,000 years. So, one thing I just want to mention is that the previous slide suggests some kind of inexorable and monotonic increase in social scale and complexity. But that's really not the case. Human evolution in the last, especially last 10,000 years, but even before, has been quite nonlinear. There are many aspects of it. But for example, if we think about categorical inequalities, right? The evolution of such structural inequalities has been very nonlinear. Our ancestral primate groups, similar to chimps and gorillas, had quite despotic organizations in which there were alpha males, beta males, and so on, that had the degree of power much greater than anybody else. And then during the human evolution, the trend was to greater egalitarianism. However, once we get to the Holocene, the trend reversed. And in fact, by roughly speaking 6,000 or 7,000 years ago, the most unequal human societies ever involved. These were complex chiefdoms and archaic states with great degrees of inequality, such involving things like human sacrifice, slavery, deification of rulers, and so on and so forth. And then there was another trend reversal, which we have not yet reached the same degree of economic equality as our ancestors during the Pleistocene, but we have been moving towards that. So I won't talk much more about inequality today because it's a big topic and I have a lot to say about it. I just wanted to bring this up to indicate that, that evolution has not been monotonic. It has been actually characterized by trend reversals and other nonlinear phenomena. So, returning to the main question of my talk, let's formulate it as the puzzle of outer-sociality. So outer-sociality is different from eusociality of social insects such as ants, termites, bees, and others. Outer-sociality is defined as extensive cooperation among very large numbers, millions and more, of genetically unrelated individuals. So cooperation between strangers and non-kin is what distinguishes our social organization from social insects. But we know, so outer sociality and degree of cooperation is a key glue holding together human societies, including historical mega-empires, such as the Achaemenid Persian Empire pictured on this slide. We think of those empires as despotic, and they were fairly despotic. But however, even a society such as a mega-empire, including Persia, Roman Empire, Chinese Han Dynasty, and others, they require some degree of cooperation amongst some people, at the very least amongst the elites. All right. Now, cooperation is very powerful, but it is also highly vulnerable to the problem which is known as free riding. So it is not enough to say that, to point to the benefits of cooperation when we are trying to explain how it has evolved and why it involves such large numbers of people. We need a credible evolutionary mechanism that would explain how free rider problems have been overcome. So how cooperation could evolve despite the destructive pressures from selfishness. So I would say that this is one of the grand questions of social sciences that does not yet have a mutually agreed upon answer. All right. So I will be offering you one answer without pretensions that it's a final word, but I think we have made a huge amount of progress towards answering this question, especially in the last 10 years or so. All right, so what I want to do in my talk is three things. First of all, I want to talk about how the conceptual framework of a new discipline called cultural evolution contributes to our investigation of the Great Holocene transformation. This is the astronomical increase in social scale and complexity over the past 10,000 years, roughly speaking. Secondly, the core of my talk will involve the overview of various data analysis that we have done, my group, research group, which is now based in Vienna, has done to answer this question. And I warn you that I will not go too much into details because different pieces of this have been published. And of course, the most complete story right now is in the book, The Great Holocene Transformation. So my goal would be to give you a bird's eye overview of research, especially over the past 11 or 12 years. All right, and if you become interested, then I urge you to consult the special publications in the books. And finally, beyond the book, Great Holocene Transformation, we have recently made more advances. So I'll talk about that in the last third part of my talk. All right, so let's start talking about what are the explanations for this dramatic increase in social scale and complexity. And there are many theories. In fact, I would not be able to put all of the hundreds of explanations that both thinkers in the past, including one of the most significant one, Ibn Khaldun, who actually lived not so far from Morocco. In fact, and he visited Morocco many times, 14th century thinker, and ancient Greeks, medieval thinkers, and more recent contemporary social scientists. They've proposed, as I said, hundreds of theories. You can do a rough classification of them by which is presented on this slide. First of all, pretty much everybody agrees that agriculture was a necessary, even though perhaps not sufficient condition for this social evolution. But beyond that, you have a variety of theories which you could classify, roughly speaking, in two groups. One of them is functionalist theories. These theories invoke some function that social complexity performs for human societies, and argue that evolution attempted to fulfill this function. So there are many different types of functions that people invoke. The opposite approach is known as conflict theories. And this opposite approach also can be divided in two. Some theorists, such as Marx and Engels and many modern-day Marxists who follow them, invoke internal conflict specifically between classes, all right? More recent theories, such as grains make states, also invokes coercion within societies. The opposite approach by conflict theorists looks to the conflicts between polities, between states and other types of political organizations. So conquest theories and warfare theories. Then there are many other theories. For example, people invoke the role of religion, such as the big gods hypothesis, and the theory that we have been investigating very closely, which is called cultural multi-level selection. So let me briefly explain this theory. This theory comes from cultural evolution. This is the new transdisciplinary discipline that arose in the last less than 50 years, thanks to the work of such people as Rob Boyd, Pete Richardson, and many others. Now, cultural evolution actually can be thought of as two subfields, similar to how biological evolutionists think about biological microevolution, which is the change in the frequency of alleles within populations, and biological macroevolution, which is evolution at the level of groups and species, and even maybe ecosystems, right? Similarly, in cultural evolution, we can distinguish cultural microevolution, which has been defined by founders such as Cavalli, Sforza, and Feldman to be the change in the frequency of cultural variants within the population. So you can see it's quite analogous to how biological genetic evolution, microevolution is defined. And then we can think about cultural macroevolution. So these are large-scale changes in cultural traits of whole groups, including states and empires. So this subfield is where my talk is squarely situated. One thing is that it is not, well, obviously there is quite a lot of connections between the micro and the macro levels, but I argue that we cannot reduce the processes of cultural macroevolution to microevolution. Because many of the traits, even though some traits, group level traits, reduce directly to individual traits. So for example, the average wealth of a population, GDP per capita, right, that is an average of the wealth of all people within a particular state. But other traits do not reduce. You cannot reduce them to individuals. So think about examples such as institutions. For example, the institutions that regulate government in states. So, for example, institutions such as the parliament, all right, or the social norms that govern democratic elections. Those traits belong to groups. There is a lot of variation between how different countries are governed. So United States and China have a very different set of governing institutions. But it doesn't make sense to say that Americans, are democratic institutions and Chinese are more autocratic institutions. These are traits which are expressed not at the individual level, but at the level of whole society. Now, of course, individual traits may have an influence. So, for example, the proportion of people who believe that governance should be democratic or otherwise That's obviously a trait that is based on individual, at the individual level. But once we start talking about institutions, it becomes a trait of emergent, it becomes an emergent property of groups, not reducible to individuals. So this is the evolution of such group level or polity level traits is what I am particularly interested in. And this is what we need to understand if you want to understand the great Holocene transformation. Let me just step back and say that the great Holocene transformation, which has happened in the last, let's say, 10,000 years, may be thought of just the most recent example of a much broader and much more abstract transformations that have been involved, for example, in the evolution of life. These are often referred to as major evolutionary transitions, and they involve the transition from protokaryotic bacteria-like cells to a eukaryotic cell depicted here, or the next transition from such cells to multicellular organisms. In fact, tomorrow there is going to be a lecture that will look at that particular major evolutionary transition. Similarly, from individuals to eusocial insect colonies, that is another major evolutionary transition. And finally, my argument is that the rise of complex human societies is the last one of those. And theorists of these major evolutionary transitions have proposed a general, very mechanism that at a very abstract level works in very similar ways in all of these transitions. And the general processes involved in these transitions first require that we think about particles and collectives. So, for example, a particle could be a cell, and collective is in organisms with many cells. All right, and so the very first step that we need to start on this process is for evolution to encourage particle cooperation. Now, the next step is that now collectives of particles have to come under selection at the collective level. And this is where multi-level selection comes to the fore, because in order for us to understand how this transition happens, we have to take into account that evolution works in opposite ways at different levels. At the individual level, selfishness destroys cooperation, whereas at the collective level, cooperation makes collectives more fit than others. So as selection on collective proceeds, it involves suppression, greater and greater suppression of particle selfishness, and within collective competition, which results gradually in increasing functional integration of collectives, at which point collectives can become organisms, and then the whole cycle can start over again. So this is sort of how the evolution of complexity in the human species can fit within a very, very broad evolutionary framework. All right, so now I'm going to go and talk only about cultural evolution. So the theory of cultural multi-level selection is proposed by me and my colleagues as a general mechanism of cultural macroevolution. The nice thing about CMLS is that it integrates functional and conflict theories, but not just like everything goes. No, it integrates them in a very specific, special ways. So the conflict, the important role of conflict is between polities. So it is intense interpolity competition that is the major force of evolution. And its result is increasing functional integration within polities. So both conflict and functional integration are important, but it is the conflict between groups. So conflict within groups, in fact, despite what Marx and Engels thought, is destructive of cooperation, according to this theoretical framework, and in fact, much empirical data that supports it. So competition between polities can happen in many ways. For example, I grew up in the Soviet Union, and the Soviet Union was not transformed, not because it lost a war with the United States. No, it lost the competition, economic and ideological competition between USSR and United States. Similarly, before the Holocene, we think that most of the competition between human groups did not take the form of warfare, intergroup conflict, violence. Rather, it was the kind of game of us versus the environment rather than us versus them. But over the past 10,000 years, we have to face it. The primary mode of competition between societies has taken violent forms, organized warfare. So warfare then has been the most important evolutionary force according to the CMLS theory during the last 10,000 years. Now, intensity of warfare has changed because technology has changed, in particular technology that affects military affairs. All right, so here what I'm doing in this slide is I'm translating two general theories of cultural evolution. One of them is CMLS, the other one is cumulative cultural evolution, which resulted in accumulation of technology, especially technology in the military sphere. So those two factors are the ones that we invoke to try to understand the transformation. Now, historical sociologists and historians have, of course, noted this. There is a huge body of work on what is known as the military revolution of the 16th century. This theory was expressed by Charles Steele as war made the state and the state made war. So you can see here a nonlinear feedback loop situation, which is, of course, betrays complexity science thinking, even though it was not explicitly said so by this group of scholars. So the idea was that military revolution, which involved gunpowder weapons and also importantly ocean-going ships, that has intensified warfare and interstate selection pressures. And that resulted in rapid cultural macroevolution. Some of the traits were relevant to warfare, such as fortification, military organization and drilling, but other traits resulted in the increase of social scale of states, because the larger you are, the bigger army you can bring to the battlefield, and the more population that pays taxes to support the state. And many other types of institutions have evolved, such as new fiscal institutions, and later, in fact, democratic institutions. There is a very close connection between military pressures and the spread of democracy. So evolutionary theory actually provides us with, especially cultural evolutionary theory, provides us with an integrative framework within which this case can be fit. But one point that I would like to make here is that the military revolution of the 16th century was not the first one, right? And not the last one, actually. We are clearly going through another military revolution right now. But before that, a very significant and very important military revolution was the iron and cavalry revolution of the first millennium BCE. What happened was that around 1000 BC, people, nomadic people living in the steppes of Europe invented horse riding. Horses had been domesticated for thousands of years before that, but it was only around 3,000 years ago when people learned how to ride them effectively, and effectively so they could be used in warfare. Now, what's important actually, it's not really horse riding in battle as much as everybody thinks about armored knights riding at each other. Yeah, that's important, but not the most important thing. It was really the logistics and supply, scouting and other new strategies that resulted in this revolution, which triggered rapid evolution of new weapons, armor, tactics, and fortifications. So in very much in a parallel way to a later 16th century revolution. And there were other military revolutions before that involving chariots, bronze, and so on and so forth. All right, so because my time is limited, I won't talk much more about cultural multi-level selection, except to emphasize that it postulates that the most important driver is interpolity competition, which during the Holocene took the form of warfare. All right, so now how can complexity science help us figure this out? We have many theories. How do we distinguish between them? How do we test them empirically, one against each other? Well, for that we need a mathematical conceptual framework. And here I use one which is very familiar to mathematicians and to people who work in dynamical science. So here, this is the form that takes a discrete time approach. So we have the system of difference equations, but of course that's closely connected to systems of differential equations in continuous time. I use discrete form because this allows us to approach data much more effectively, as you will see in a moment. So the idea here is that we represent different characteristics of polities, and here is the definition of polity. Polity is an independent political unit, which could be a self-governing village, a simple or complex chiefdoms, a state, or an empire. So it's a political organization. Now, and I prefer to use polities rather than societies because society is too vague a term. All right, so to do cultural macroevolution, we want to understand how properties, how characteristics of polities change in time. And so here in this framework, X, for example, could be social scale, just what is the polity population, for example. And Y could be a measure of institutional complexity, and so on and so forth. And so the idea here is that the evolution involves, first of all, cultural characteristics of polity that could be thought of as endogenous variables, which means that they are part of feedback loops. That's why in the first equation, xt plus 1, first of all, depends on itself, right? Because you evolve from where you started from. But it also is affected by other variables like y, z, and so on and so forth. In addition, we have exogenous factors that are not part of the feedback loops, which could be modeled as noise or as a sharp transition or what have you. And f, g, and h are functions specifying how variables interact with each other. So this is a very familiar framework to, I'm sure, people here. All right, so the nice thing about this framework is that now we can use it to classify all those different theories by, first of all, what is the response variable, right? So what is on the left-hand side, x, y, z, and what are the driver variables or the explanatory variables. These are the ones within, on the right-hand side, within the parentheses. And so every theory, first of all, is trying to explain something. Some theories try to explain the evolution of the state. Others talk about centralization. The cultural multi-level model, for example, focuses on how social scale increases. So that tells us what is the response variable. This is what we are trying to understand. And then each theory has its own mixture of explanatory variable. So the idea here is quite simple. What we need to be able to test those theories, variety of theories, is to gather data, time-resolved data, time series data, on both the response variables and potential driver variables. So this nonlinear dynamics framework is quite useful because, first of all, it captures the nature of the evolutionary process, right? Because we have both descent, right? Xt plus 1 depends on xt, but also modification, because yt, zt, and so on also affect how x changes, all right? And it is, mathematically, it's very general. It includes all kinds of different behaviors, including quite esoteric ones like chaos and so on and so forth. So it's a very nice general framework within which we can directly compare different theories. And then we just take the system of difference equations, turn them around. Instead of using them to predict, for example, in a model how a system would evolve, we now do the inverse problem, and we ask how we can fit models to estimate the influences of different factors. So this is a bit more complicated. I won't go in details, but now the response variables is on the left-hand side. It depends on itself. There could be a variety of time lags. Then there is some potentially spatial component. There could be influences due to shared phylogenies, which is specific of cultural evolution. And then, of course, the drivers and noise terms. So again, this is a fairly familiar system of nonlinear dynamic regressions. So this formalism allows us to approach the question of causality. And I define causality here in a very specific way. So if you want to ask me, what causes what? I say, okay, let's give me a model that works, that actually predicts data well. And then by looking at the equations, I'll tell you what causes what, all right? So here, once we have gone through this process, we determined which y's and z's are important on the right-hand side. To me, that would be the definition of causality. Now, remember that causality is, there are many different notions of causality, so I'm not claiming that I'm doing all of them, just a very specific one. But given time-resolved data, we will be able to distinguish between 4 different scenarios that could give rise to correlation between x and y. So let's say we have correlation between x and y. It could arise as a variety of ways. First of all, there could be causal influx of x and y. So we see xt causes yt plus 1. So I'm explicitly bringing in the time component. Or vice versa, it's y that causes x. Or it could be mutual causation. Having time-resolved data allows us to actually break the curse of endogeneity, right? And then finally, it could be spurious causation because there is actually another factor, third factor, z, that causes both x and y. So we need time-resolved data to do it. And this is what the data bank project was mentioned earlier. It's called Seshat. Seshat was the Egyptian deity of scribing. information, databases, and things like that. And this project has started in 2011, so it's been going for 15 years now. And the goal of this project was actually, there were many goals, but one, the most important one for today's talk, it was to gather a big database of time-resolved variables proposed by different theories, both as both as response variables and as driver variables. And so that's what we did. We have put in the public domain huge chunks of Seshat data. You can go to seshat-db.com to browse through it and see how it goes. So I will not spend more time on where the data comes from, just to say it's a pretty massive database. At the latest data release, Polaris 2025, which we have just completed finally, there is more than 1,000 historical polities, past societies that span the globe and span the last 10,000 years. All right, so this has been published, so I'll just show you the highlights. What we did in this article, we took Seshat data and we tested 17 different proxy variables as potential drivers of social complexity. And we used 3 different response variables. These are the columns on the right-hand side, such as scale, hierarchy, and governance. So let's see. Yeah, I didn't put. So scale is simply, think about it, it's a first principle component of log-transformed polity population, polity territory, and population of the largest settlement. So, but the best way, the simplest way to think about it is simply log 10 of population, of polity population. Hierarchy is the average number of levels of hierarchies in military, administrative, settlement, and religious hierarchies, and governance is a variable expressing the sophistication of governance. So we have 3 different response variables, and we have, as I said, 17 potential predictors which can be grouped in about 5 general classes of theories. So the green ones have to do with agriculture, the blue ones is functionalist theories, then you have another kind of blue for scalar stress, which is scale-based theories. Orange is internal coercion, yellow is religion, and red is external conflict, warfare. So we have quite a bunch of different theories. And we have essentially tested them against each other by looking at which of those predictors turned out to be important. And the result was quite striking. As you can see, only the green and red lines had effect that could help us predict the next time step. All other theories, you see, blips here and there, as you would expect when you test many different theories. But other theories were not supported, right? So the best fitting models were similar also for all 3 response variables, and they fall into 2 classes, agriculture and warfare. What's interesting is that we actually achieved a high out-of-sample prediction accuracy. So let me illustrate it with 2 slides. First of all, what I'm showing here is for each of the 3 response variables, I plot simultaneous correlations between them and 2 major drivers. One of them is the MilTech, which is the sophistication of military technologies. The other one is Agri, which is the agricultural productivity in tons of carbohydrate crop per hectare per year. And you can see that, especially with military technologies, there is quite reasonable correlation, right? But what we're interested is we want to dig deeper than correlation, and so we build models. And when we build models that predict each of these three variables, so now we are predicting xt plus 1 depending on xt and then yt and zt, all right? Also, this is, we use k-fold cross-validation here. So obviously, as everybody knows, in simple regression, the more variables you include, the higher will be R squared. But when you do cross-validation, you get a much better estimate of what is the optimum complexity of the model, because if you include too many variables, you start fitting noise and your degree of correlation declines. So here we did tenfold cross-validation because our world is divided in 10 regions, such as South America, North America, Europe, Southwest Asia, South Asia, East Asia, Africa, Oceania, and so on and so forth. Hopefully this is not going to short out. All right, and so what we do here, we have 10 regions, so we emit data from one of these regions, fit the model on the 9, right, and predict that emitted region. And then we do it for all of them, and then calculate overall prediction R squared, all right? So that, because this is, this methodology gives us a much better estimate of what is the accuracy of prediction. And I was surprised. I mean, we get accuracy around 0.9, a little bit more, a little bit less for different variables, but it's quite remarkable that that history has so much regularity in it. It's amazing. I mean, you fit the models on, on Eurasia, for example, and you predict South America, right? So quite well, and vice versa. History is not really one damn thing after another. While there is a lot of variation, history actually can be understood, modeled, and to a degree predicted. So here's what our understanding of causality is currently, and there's a lot of caveats which I'm happy to discuss later on. This is very much work in progress. I don't say that we have, this is it. We are bringing more data, better analytical methods. Other people are suggesting novel hypotheses. So this is, in fact, there was a group at Santa Fe Institute who has seen more interesting patterns. Actually, I'll be referring to them in a minute in our data. So because the data is very rich, and we have not completely explored it yet. Okay, so I need to finish in the next 5 minutes. So what I'll do now is, first of all, I won't go into details, but I'll just say that in addition to this large N analysis, we have done a lot of other studies. So for example, we looked at the effect of how iron cavalry revolution affects social scale by using the empirically estimated equation and then comparing it to data. We looked in detail how the spread of iron and cavalry affected the rise of large-scale societies. So for example, here in this slide, you can see how depending on the timing, especially when cavalry has spread to a region, there is a very tight, it takes like between 300 and 400 years from the time when cavalry spreads to the region to see the first mega empire, which is defined as a state controlling then more than 3 million kilometer squares. So so horse riding spread to the central region, which is Iran and Mesopotamia, very early, and that's where the very first mega empire arose. And it spread to eastern and western ends later, and as a result, mega empires there arose somewhat later. And of course, then we rely on things like natural experiments. Horses actually evolved in North America, but then when humans came, they exterminated them. So horses next appeared in the Americas after 1492. And then, as soon as they spread into the Great Plains of North America, we saw a very similar situation arising there as we see on the borders of China or Iran, specifically the new Comanche Empire. Right, I don't have time to talk too much about it, but I do want to mention that, remember I said that, gunpowder revolution was not the first, not the last one. So here is another look at using an alternative measure of scale. This is the log transformed area in squared kilometers that is controlled by the largest empires extant at any given time. And here you can see that the introduction of bronze resulted in a brief appearance of empires which, though quite quickly collapsed. Then chariots resulted in a more elevated level, still quite fragile. Iron cavalry gave us another jump. And notice how for the 2,000 years after this transition, the scale did not change. There was just fluctuations around it. And the last kick was gunpowders. All right, so the final thing, I've got about 3 minutes, that I want to go through is the new results that we've got in the last half a year or so. Many of you are familiar with the main sequence of star evolution, where we know that about 90% of stars, known stars, belong to that main sequence, and we have a pretty good understanding what happens there, that they progress through this curve by burning hydrogen. In addition, there are alternative routes, such as white dwarfs or big giants and things like that. Now, what's interesting is that now we have a lot of data. And we have, as I said, we have 1,000, roughly speaking, 1,000 polities spanning the globe and the last 10,000 years. And if we plot them in this phase space where on one axis you have scale, and as I said, it's the PC1 of log transformed population, positive population territory and capital size, and then comp. Comp is integrates 44 different institutions involved in governance, information processing, economic exchange, provision of public goods, and things like that. So it's scaled to be between 0 and 1. 0, essentially, you have none of those sophisticated institutions, and 40 and 1 means you have all of them. So when we plot data in this way, what we see is very interesting. Well, first of all, of course, we see that there is correlation between collective computation capacity and scale. But there is much more going on here. There is all kinds of nonlinear features. So for example, note that the lower blob and the color here indicates the density of points. Because there are so many points, it's kind of hard to tell without some help where they are more dense. So we see sort of the lower blob is mostly extending from left to right, which means that the hypothesis is that these polities move from lower scale to higher scale. And by the way, the way they move, the two forces that impel them to move are, first of all, agriculture, and secondly, military technology, including military revolutions. Right, yeah, I'm finishing. So, and then there is transition, and there is a larger blob. The other interesting feature is the forbidden corners, those blue corners that are both in the upper left and lower right. Again, but what's interesting now, let's get some dynamics in it. So now, what we did, we broke this phase plot into squares, and for each square, we look at all the polities that are there and look at what happened to them at the next time step. So that gives us a bunch of vectors, and we average those vectors using vector algebra, all right? And that's what the arrows indicate. The thickness of arrow indicates how many polities are going there. And what you see here, let me just put some arrows here. What we see here is very similar to the main sequence, all right? The polities, and it's nonlinear, the polities first move to the right, they gain in scale. But then once they get to a pretty high scale, so 5 or 6 means 100,000 or million, they suddenly impelled to move up, like going up the chimney. And then they more gradually converge to the next one, the next blob in the upper right. On top of that main sequence, there is a lot of interesting variations. So I show here imperial confederations are the ones of steppe nomads, for example. They get very large in scale without much institutional complexity. And then they realize, I've got to have, once you're Genghis Khan who conquered China, you realize that you cannot govern from the horseback. You have to get, significant institutions working. And the other alternative involves city-states. Okay, so just to finish up, first of all, as I said, quite a lot of this is, except for the last 3 slides, is in the book. All right, I want to acknowledge my wonderful group at Complexity Science Hub in Vienna. And here are just some conclusions. I'll just say that, just to look at the last thing, that the cumulative cultural evolution and cultural multi-level selection, the 2 processes which are supported by our abundant data analysis and modeling as major drivers of the great Holocene transformation. Thank you very much.
Can you hear me? Yes, thank you, Professor Turchin. Thank you for your talk, and sorry to sort of push you to the end, but as we've started a bit late, we're going to try to catch up a little bit. Maybe the questions, we'll keep them really short, maybe just 1 or 2. I actually have one sent by Professor Nemish, who can be here today. So obviously he hasn't seen your talk right now, but he had this question for you, so I'll just ask it and see if it, if you can just speak onto it. So he says, in your theory of ultra-sociality, you emphasize warfare and initial geographic conditions as key drivers of social complexity. However, since the Industrial Revolution, technology and global economic institutions seem to have fundamentally reshaped these dynamics.
I would argue that actually the latest military revolutions, certainly the 16th century revolution, reshaped the technology and economics, but it did not change the nature of competition within societies, unfortunately. Even though our analysis points to warfare as the major driver of progress, this is to me a negative thing. And one thing to understand from cultural multi-level selection is that it's not killing people. It's competition within societies. So, for example, the competition of firms in the marketplace has exactly the same nature, or competition of scientific groups. So we need to make this transition to non-violent competition between societies. But we have not done so far. And latest results, especially the war in Ukraine, the war in Iran, and so on and so forth, show that we are still, that warfare continues to be a major driver of progress. And we are now in the next military revolution. The drones and AI is reshaping things, and it's putting huge pressures on societies governments to change their institutions and to change the way they operate in order to survive in this competition. So I would say that unfortunately we are still in the same general situation.
Maybe I'll take just one question. Yes.
Yes, thanks for this very nice, fascinating talks. David Chavalarias, when you have your descriptions of different scales that we go through societies, don't you think that now social networks are adding another scales where now, for example, when you have Facebook with 3 billion users, or these kind of orders, so do you think that we have unlocked another scales of our social organization, and what you would expect from this phenomena?
Yes, obviously, because my time was short, I could only focus on the social scale of politics. But remember that states, which is an alternative route to the main route. Now, how did those, this is where, for example, ancient Greece, like Athens was. How did they get so high in the computational capacity? That was because there was another scale. They were part of interacting peer polities. So Athens was interacting with Thebes and others. Or in northern Italy later, we have Milan was interacting with Venice and Florence and so on and so forth. So what I would say that, in answer to your question, that nothing is new under the sun. The social networks right now, maybe as a result of technology, we can communicate faster and more efficiently, but it's a quantitative, not qualitative difference. So these networks of interaction, especially, for example, the Great Silk Road, which was a major artery of not just trade, but the movement of ideas and genes, cultivars, and so on and so forth. So that was a result in progress of globalization at the level of Eurasia. So I would say that the lessons that we learn from the past 10,000 years are highly relevant to us today, but of course our specific models will take into account the details of how social networks are constructed and how fast information spreads through them.